Okay, now in our methods of integration, we've talked about trigonometric substitutions. So we're going to give some rules of thumb. Our first case is a squared minus x squared. And in this case, we want to choose x equals a cosine theta or x equals a sine theta, one of the two. And dx for both, this one would be minus a sine theta d theta, and this one would be a cosine theta d theta. Now, of course, we're using the cosine squared theta plus sine squared theta equals 1 identity. So when we plug in our variable substitution, we have a squared minus a squared sine squared theta. And out here, wherever there would be a dx, we would have a cos theta d theta, something to that nature. Yeah, that would be right. And this, we would pull out the a, and we have 1 minus sine squared theta, which that would be square cos theta d theta. And 1 minus sine squared theta is cos square, but you got a square root, so we have a squared cosine theta times cosine theta is cosine squared theta d theta. So you would have something of that nature. Now our second, we would have to straighten that out. Second situation would be the square root of a squared plus x squared. And in that case, we would be using x equals a tangent theta, and then dx would be a secant squared theta d theta. And of course, we're using 1 plus tangent squared theta equals secant squared theta. That's the identity we're using. And so that would lead us to a squared plus a squared tangent squared theta times, now the secant squared theta, so a secant squared theta d theta. And again, we would pull that a out from the square root, so we got a squared, and 1 plus tangent squared would be secant squared theta. So we would end up with secant to the third theta d theta, which is a special case. That's going to take quite a bit of integration. Our third case would be the other way around, where we have x squared minus a squared. Now, in that case, we would use x equals a cotangent theta, and dx equals minus a cosecant squared theta d theta. and we're using the identity cotangent 1 plus cotangent squared theta equals cosecant squared theta. And in this case, we would have A cotangent squared theta minus 1 times, that would be A squared, a negative sign, cosecant squared theta d theta, and we do the same thing down here. So we have 1 minus A squared cosecant to the third theta to d theta, and that would be analogous to, it's just a special case of number 2. In fact, actually, when we look at number 3, we could say that x squared minus a squared is equal to the square root of negative 1 times a squared minus x squared. And then we would use the trig substitutions for this condition. We would have I, which is the square root of negative 1, a squared minus a squared sine squared theta. So we could do it that way, but then we have an imaginary number, and it's going to be a little cumbersome working with that. So there are various ways of dealing with this, but these are generally the 3 rules of thumb: this case, that case, and this case up here. And then, of course, we don't want to forget that we have very important identities, the double angle formula. So we have cosine of 2 theta equals cosine squared theta minus sine squared theta. And when we work that out, we can have either 2 cosine squared theta minus 1 equals cosine 2 theta, and that would be 1 plus cosine 2 theta on 2 equals cosine squared theta. Or we would have cosine 2 theta equals 1 minus 2 sine squared theta. And so we have 1 minus cosine 2 theta on 2, and that would equal sine squared theta. So we have these double angle formulas for the cosine function that can be substituted if we have these in the integrand, cosine squared theta or sine squared theta. This has quite a bit of utility. Also, another very useful trigonometric identity is the double angle formula for the sine function. So if we have sine of 2 theta, that's equal to 2 sine theta cos theta, and often that helps us in our solutions or in our integrands. So we have a variety of trigonometric tools that help us when we do our integrations. Now, here's a circumstance where we're going to pick up from our last example, and we're just going to continue doing some interesting integrals. And in this case, we've got a definite integral. So we've been given 0 to a dx over a squared plus x squared. And in this case, we realize that this is the case where we use x equals a tangent theta, and dx equals a secant squared theta d theta. And so we go to our next line. We go 0 to a. Actually, those aren't our true integrals. We've got, we'll say a to b. We don't know. Those are dummy variables. And so we have a squared a secant squared theta d theta in the numerator, and in the denominator we have a squared plus a squared tangent squared theta. And when we pull out the a squared, we've got 1 over a to b secant squared theta d theta, and the denominator is secant squared theta. Those cancel, and we have 1 over a and d theta, a to b, and that's 1 over a theta, evaluated from b to a. Now, theta, we know is x over a equals tangent theta, so arctan of x over a is theta. So we plug that back in. 1 over a arctan x over a, and we put our original limits, a to 0, and that's equal to 1 on a tangent or inverse tangent 1, a on a, minus arctan of 0. This is where we find out what our angles are. So we know that the arctan of 1, so we have 1 equals tangent theta, which is sine theta over cosine theta. So sine theta must equal cosine theta in order for that result to be 1. And that happens to occur when theta is pi on 4, or 45 degrees. So we know that 1 on a times pi on 4 minus 0. So for tangent theta equals, we got 0 equals tangent theta sine theta over cos theta, then sine theta must be equal to 0. And that happens at 0 degrees. so that's minus 0. And the result is pi on 4a. And that's our integration, a definite integral, using a trigonometric substitution. Now, we got some pretty interesting ones coming up. Let's take a look at the next. Alrighty, let's take a look at what we've got. Okay, alright, why don't we look at this? This one looks interesting. Another definite integral. Okay, so our integral is 0 to a dx over a squared minus x squared, or plus x squared. It looks similar to the previous problem, except we got a square root here. So that leads us to a different result. So here we got x equals a tangent theta, and dx again is a secant squared theta d theta. So we put that substitute in. Again, we have, I'm going to leave the limits out because we know we got limits, and I don't want to play around with just writing them. They're right now they would be dummy limits anyway. So what we're going to do is we've got dx is equal to a secant squared theta d theta, and we've got the square root of a squared plus a squared tangent squared theta. And the a cancels out, so the a's disappear. We've got secant squared theta d theta over, and this is secant squared theta, under the square root, so that's secant theta. And that leaves us with an integral of secant theta d theta. And this is, whoops, I keep twisting that. Okay, so between limit 1 and limit 2. Okay, so which we're just going to leave alone right now, because when we go back to x, we'll put in the original limits. So now we've done this integral before. We multiply the top and bottom by secant theta plus tan theta over secant theta plus tangent theta. That's simply 1 d theta. And we multiply through 1 to 2. And we got secant squared theta plus tangent theta secant theta d theta. And that is over the natural, oh, sorry, I'm jumping ahead. Secant theta plus tangent theta. Now, we do a u substitution. we go u equals secant theta plus tangent theta, and du equals secant theta tan theta plus secant squared theta d theta. And that's what we have in the numerator. So we have 1 to 2 du over u, and that's equal to the natural log of u, which is secant theta plus tangent theta, and evaluated between 2 and 1. But secant theta, so here we've got to do a little trigonometric, right triangle trigonometry. Here we know we got tangent theta equals x on a. So we have x, a, and a squared plus x squared under the square root. So here we've got the natural log of secant. So the secant theta is the square root of a squared plus x squared over a plus tangent plus x over a, evaluated between a and 0. And if we carry that out further, we have what was that? A. Zero and a. So we have the natural log of 2a squared, so square root of 2 plus 1 minus the natural log of 1 plus 0, and so that is equal to the natural log of square root of 2 plus 1. And that's our answer. The natural log of square root of 2 plus 1. Oh. Yeah, because this is a division here. Here we have this really stands for ln square root of 2 plus 1 over 1, because ln of square root of 2 plus 1 minus ln 1 is just a division by 1, so this is the answer, the full answer. Okay, so let's take a look at another. Okay, here's an interesting one. This one's very interesting. I'm gonna put this thing on here so it's easier to write. Makes it a little higher. Okay, now Here's an interesting problem. We got a definite integral, 0 to 1, of dx over x squared plus 4x plus 5. Now, here, we're going to do something where we're going to square the denominator. So here we have x plus 2 times x plus 2, and that gives us x squared plus 4x plus 4. That's not quite what we've got in the denominator. So we have to say this is x squared, or x plus 2 squared plus 1, and that gives us the x squared plus 4x plus 5. So now we go to 0 to 1 dx over x plus 2 squared plus 1. Now we can use our trigonometric substitution, where x plus 2 is equal to sine theta. In fact, we're not going to use sine theta. It's tangent theta, because we got a plus in there. So that's tangent theta dx equals secant squared theta d theta. And now we've got 0 to 1 secant squared theta d theta in the numerator, and in the denominator we have tangent squared theta plus 1, but that's equal to secant squared theta. So we have in the numerator and the denominator we have secant squared theta d theta over secant squared theta. That cancels, and we end up with 0 to 1 d theta. Again, these aren't the real limits. I didn't go to bother to calculate them because I'm going to be I'm not going to substitute new limits for the dummy variable. I'm going to go back to the original x variable, and so I will use the original limits when I finally do the evaluation. So here we end up with theta, and it's evaluated between some a and b, all right? Just to be technical. So theta in this case is x plus 2 on 1 equals tangent theta. But if we take the arctan of that, then we have theta and x plus 2 over 1. And so we have arctan of x plus 2 evaluated between 1 and 0. And that gives us the arctan of 3 minus the arctan of 2. And that's the best that we can get at this point. We can't be more precise than that. We don't know what that's what angles are going to give us those results. We'll just leave it at that. So that looked like it might be a tough one, but it really didn't work out to be tough at all. Now, here comes another one. Now, here is a really good one. This is a very good integral. And we're going to have to do it by parts. We're not going to do it by trigonometric substitution. X squared e to the x dx. And what's interesting about this problem is that we're going to have to use 2 integrating by parts to get the correct answer. So here we're gonna say u equals x squared du equals 2x dx, v equals e to the x, and dv equals e to the x dx. Now, we use our integration by parts formula, which is simply u v equals v du plus u dv. So u times v is x squared e to the x equals u dv, so x squared. dv is e to the x dx. As you can see, that gives us our original integral, plus 2x e to the x dx. Now, this we need to use integration by parts again. So let's call our variables p and u. So we'll say p equals x, dp equals dx, q equals e to the x, dq equals e to the x dx. And so if we go to the side here and evaluate, we got x e to the x, and that would be equal to x e to the x dx plus e to the x dx. And so our integral x e to the x dx equals x e to the x minus e to the x and plus c. So now we've got this resolved. We go back to our original function, e to the x equals x squared e to the x dx plus 2, and that is multiplied by x e to the x minus e to the x plus c. And now we do all our rearranging, and we end up with x squared e to the x dx equals x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Now we can simplify this a little more by x squared e to the x dx equals, now we pull e to the x out, e to the x times x squared minus 2x plus 2 plus c. We could either leave it like that or try and simplify it a little more. So let's say e minus 1 times x minus 1, that's x squared minus 2x plus 1. So we have e to the x times x minus 1 squared plus 1 plus c. And that's our final solution. So we have x squared e to the x dx, and that's our answer. So that was an interesting problem. And now here comes one that is even more complicated. It's similar, but it's going to require us to be a little bit more attentive. So let's see here. Yeah, this is going to be a pretty cool one. It looks like it's impossible, but it isn't. We've got x squared e to the x to the third. So our first thing to do is we choose u equals e to the x to the third, and du equals 3x squared e to the x to the third dx. V equals x squared, and dv equals 2x dx. But we don't need to do that. We don't need to use that at all, as a matter of fact. We don't need what we've got all we need at this point, because du equals, let's see, du on e to the x to the third equals 3x squared dx. In fact, what we're going to do is this. I'm going to erase that. We've got du equals 3 we've got all we need here right at this point. All right, let's not make this too difficult. So we've got our two problems here. So we got du on 3 equals x squared e to the x to the third dx, and that's what we got there. So we have basically du on 3. It looked like a tremendously complicated integral, but it wasn't complicated in the slightest bit. It's simply 1/3 u plus c, and now 1/3, and we take our substitute out. We've got u equals e to the x to the third plus c, and that's our answer. So this complicated looking integrand really turned out to be quite simple. And that is our result. Sometimes these things can really fool you. They're not as bad as you think they are. Now, here's one. Let's take a look at this. This looks like an interesting one. So let's try this. We've got dx over 1 plus e to the x. So we use a u substitution equals 1 plus e to the x du equals e to the x dx. And so du let's try something here. Let's be careful about what we're doing. So let's dx all right, so we have e to the x so we got du on e to the x and u, but we have e to the x equals u minus 1. So we have du on u times u minus 1. Okay, so now we use partial fractions to be able to solve this. So we have 1 over u times u minus 1 equals a over u and plus b over u minus 1. To simplify it, now we multiply across. We got 1 equals a times u minus 1 plus b times u. And if we choose u equals 0, we have 1 equals negative a. So negative 1 equals a. And if we have 1 equals negative u minus 1 plus b times u. If we say u is 1, we have 1 equals b. So now we have two integrals. We have du over u minus 1 minus du over u. And that is simply ln u minus 1 minus ln u plus c. And this is now using the logarithm identities. We have ln u minus 1 over u plus c. And then we go back to our original variables, where u is equal to 1 plus e. So 1 plus e to the x minus 1 over u, 1 plus e to the x plus c, and that is equal to the natural log of e to the x over 1 plus e to the x, and that's our final answer. Now let's just check it and see how we got it. Yeah, that's exactly the result. And this was kind of an interesting problem because it's one of those cases where partial fractions really helps us to solve this problem. So, are you interested in more television?
I guess so.
What?
I guess so. I have so many things I have to
Uh. What? Oh, we could try it tomorrow.
Need someone to lift the shit out of the basement. I'm gonna get rid of your chest of drawers and use the one in the basement. It's identical to the one in the
All right. Now we're gonna Did you want to turn on the TV or should I keep going?
How much do you have left?
Well, I got a couple, just 2 more, all right?
How long is it gonna take?
What?
How long will it take?
10, 15 minutes? At the most. All right, so I'll just do it, okay? Here we got an interesting problem. Whoops, I didn't choose the right pen. Okay, we got the arctan of x dx. Now, what do we do with that? We got theta equals the arctangent of x. And so, tangent theta equals x, and secant squared theta d theta equals dx. And so we make this substitution. We've got theta, secant squared theta d theta. Now what we do here, we're going to be using integration by parts. So what we're going to do here is we're going to say u equals theta, du equals d theta, and v equals tangent theta, and dv equals secant squared theta d theta. And now we use our uv trigonometric method, integration by parts. So we got theta, tangent theta equals u dv. So we have theta secant squared theta d theta plus v du. So we got tangent theta d theta. And tangent theta is sine theta over cosine theta. And if we say u equals cosine theta, du equals minus sine theta d theta. So we have here theta secant squared theta d theta minus u du. So we got u du, and that's theta secant squared theta d theta minus the natural log of u. And now we do some rearranging. We've got theta secant squared theta d theta equals theta tangent theta plus the natural log of u, but u is cosine of theta, cosine of theta. And now we go back to x. This plus c. Now we go back to x. Now x, tangent theta is x, so theta is equal to tangent, we got arc tangent theta times x, let's see, theta, tan theta is x. I wrote this incorrectly because we're going to our original variables equals x tangent x plus the natural log of cosine of x. So we got to go here where tangent of theta is x over 1, and we got 1 plus x squared, and so cosine is 1 over the square root of x squared plus 1 plus c, and that's our final answer. That was a really interesting problem. That is a pretty wild integration. And you're not going to see that worked out in many books. But we've got that. We've got that worked out exactly, perfectly. So that is so cool. That is so neat. Now we're going to do, you know what? We're going to leave that as our last problem at this point. So with that, we're going to keep this video relatively short, and until next time, everybody stay safe.
I'm sorry, you can keep going.
No.
This is a shit magazine.
You sure? I got one more problem I could
Go
do.
for it.
All right, we're going to do one more problem here. So let us close out this. And this next problem is actually going to be one of the tougher problems that you'll ever encounter. Probably one of the most challenging problems that a student will face. In fact, in calculus, in integration techniques, this may be, it doesn't look like it would be, but this may be the toughest problem you'll encounter in college. So we have a squared plus x squared under the square root dx. And here we just use a trigonometric substitution where x equals a tangent theta and dx equals a secant squared theta d theta. Whoops. You know what? I'm going to write that out down below. we're gonna, okay. Dx equals a secant squared theta d theta. Now, we make our substitution. We've got square root a squared plus a squared tangent squared theta times a secant squared theta d theta. And now we pull out our a's. We got a squared on the outside. And our integral now looks like 1 plus tangent squared theta times secant squared theta d theta. And we know that under this square root, we've got 1 plus tangent squared theta equals secant squared theta. And because that's under a square root, we have a squared secant to the third theta d theta. Now this is the part that is the most challenging. Right here, secant to the third. This is one of the more difficult integrals that you'll encounter in college. And we're going to try doing this. We're going to solve this using integration by parts. So, again, it comes down to selecting the right variables for integration by parts. So u and v, let's use u equals secant theta, du equals secant theta tangent theta d theta, and v equals tangent theta, and dv equals secant squared theta d theta. So, multiplying across, we've got secant theta tangent theta equals and remember, everything is multiplied by a to the third, or a squared. So we can't forget that a squared. That's something that we got to keep our mind on. We can't forget that. So let's look at this here. We've got u dv, which is secant to the third theta d theta, plus v du, so that's secant theta tangent theta, and that's square d theta. Now, let's see what we've got. Tangent squared. Let's see if we use 1 plus tangent squared theta equals secant squared theta. That would lead us to I don't know if that's the right route for us. Let us just organize things around. So let's get secant to the third theta d theta equals, and a squared there, so equals a squared secant theta tangent theta minus secant theta tangent squared theta d theta. Now, we've got this integral to solve. Oh, we forgot our a squared. There. Now, let us take a look at what we've got. We can go back to some original identities here. So if we have secant theta equals 1 over the cosine of theta, and tangent squared is sine squared theta over cosine squared theta. So we have a squared secant to the third theta d theta equals a squared secant theta tangent theta minus a squared. Now we have sine squared, which is now we got cos squared theta plus sine squared theta equals 1. So we got 1 minus cosine squared theta over cosine to the third theta d theta. And now we break this up into two integrals. We've got a squared secant to the third theta d theta equals a squared secant theta tangent theta minus a squared secant to the third theta d theta plus a squared secant theta d theta. And now we know how to do secant theta d theta. We have that. So this term can move over. So we have 2 a squared secant square third theta d theta equals a squared secant theta times tangent theta plus a squared secant theta d theta. Now we solved this one multiple times, so we know how to solve this one. This one we multiply top and bottom by secant theta plus tangent theta secant theta plus tangent theta, d theta, and we multiply through. So we're going to, for saving space, we're going to do this like this, so I don't have to. This will be secant squared plus secant theta tangent theta d theta over secant theta plus tangent theta. And now we have u equals secant theta plus tangent theta, and du equals secant theta tan theta plus secant squared theta d theta. So we have u du on top. So we got a squared secant to the third theta d theta equals a squared. You could see why this is a involved integral. It takes a lot of doing, a lot of tricks, math tricks to, or manipulations to a du over u, and that's just the natural log. So we have 2a squared secant to the third theta d theta equals a squared secant theta tangent theta plus a squared times the natural log of u, which is secant theta plus tangent theta plus c. Now we've got the whole thing solved. All we have to do is go back to the original variable. Now you can see this is quite, this integral secant to the third theta d theta a squared equals a squared on 2 secant theta tangent theta plus a squared on 2 natural log of secant theta plus tangent theta plus c. Now, all we have to do is go back to the original variables, and we've got it. So, what we're going to do is this here is the original integral equals a squared on 2. Now secant theta, we have to go back to some trigonometric identities here. So here we said that x on a was tangent theta, so that's a squared plus x squared. Secant theta is the square root of a squared plus x squared on a times tangent theta, which is x on a, but the a's cancel out, so these go out, and this becomes 1/2. And we gotta, let's just make this a little neater. We got 1/2 a squared plus x squared times x plus a squared on 2 natural log of secant again, which is square root of a squared plus x squared on a times, or let's see, plus, what am I doing? Not times, it's plus. Plus tangent, which is x on a, plus c. And that's our answer. There we go. We have solved that integral, and that is a very complex integral. It's probably one of the most difficult integrals that you'll encounter. Graduate school. When you get into graduate school, you're not going to find a problem this elaborate. We just solved probably one of the hardest integrations that you'll ever face. So you got the tools, you got the knowledge with your understanding of trigonometric identities and how to choose proper substitutions, and the methods of integration using, in this particular case, where we used the integrating by parts. Actually, we used 2 methods. We used substitution, trigonometric substitution, and then we used integration by parts, and then we went back to putting the everything back into the original variable x. And so we have all of the we got everything here. It's really pretty cool. This is a pretty cool problem. So anyway, we're going to leave it off here at this point. And we'll pick up on integration techniques in the next video. In fact, we're going to be doing a lot of integrals, and I'm going to create a video that indexes the different integrals that we have solved. So it will tell you what integral we solved and what video you can find it in, which by identifying which video, and I'll try and see if I can put a time mark also as part of the index, so that if you have a particular problem that you're interested in, you'll be able to go right to it. But that's ultimately the goal. It's going to take a while to get there. Right now we're just solving integrals, and then we'll worry about the index later. So you can be pretty proud of yourself for tackling this problem. This was not a trivial problem. And if you notice the integrand here, just one last note, the integrand of this integral is from the Pythagorean theorem. So this is not a trivial integral by any means. The Pythagorean theorem is something that we run into time and time again. It's one of the most important mathematical relationships that we will ever encounter. And it's and being able to solve that problem, the Pythagorean theorem as an integrand to an integral is pretty phenomenal. So with that, I bid you adieu, and be safe.